Okay, now we're going to talk about population means, and we'll want to get to confidence intervals and hypothesis testing just like we did for proportions. So the story for population means is similar to the one for proportions. If population, now we're going to measure a quantitative variable, has mean mu and standard deviation sigma, then the collection of all the sample means, x bar, that this collection is called the sampling distribution of the mean, is normal, even if the original population wasn't, has mean mu, and has standard deviation sigma over the square root of n. And there's a lot going on there, but from those three facts, we'll get confidence intervals and hypothesis testing. So here's an example. Here's a histogram showing the assessed value for 3,000 houses in Wisconsin. The mean is 274,000. The standard deviation is 220, almost 4,000, 224,000. That's definitely not normal. It's very skewed. We can see this tail going off to the right. It's a little hard to see, but we can see it. So this is the original data. Now suppose we send 1,000 researchers out into the community, the community from which these homes were taken, and they each look at 100 houses, and the numbers they report back are the sample means. That's what this histogram is. So these are 1,000 sample means. Each sample is from 100 houses. So the way to think about this is you had a huge statistics class at the university with 1,000 students, and each student was sent out to take a random sample of 100 houses and just report back the average of those 100 houses. So, and then this is a histogram of those 1,000 averages of 100 homes. Well, the mean is still 274,000. Now the standard deviation is much smaller, 21,349. That's because we divided by the square root of the sample size. Square root of 100 is 10. And this, as you can see, is pretty normal looking. So that's the idea, that even if the original data is wildly skewed, when you look at all the things that could happen when you take sample means, it won't be skewed, it will be normal, and the numbers will be closer together. So let's look at another example. So let's look at a specific example. Suppose at buystuff.com, the mean size of an order is $200, and the standard deviation is $30. And we want to know what's the probability that a single order is for less than $212. So here we're not talking about sample means anymore. We're just talking about one single order, and we'll assume that the orders follow a normal distribution. Well, we find the z-score that goes with 212. Subtract off 200, divide by the standard deviation of 30, we get 0.4. Put that into norm dist. And there's a 66% probability, or 0.66 probability, that a single order is below $212. And I see a typo here. That's supposed to be $212, not $21. Now, what's the probability that the mean of 25 random orders is less than 212? Here's where we use our theory about the sampling distribution. Recall that the collection of sample means is normal, has mean mu, has standard deviation sigma over the square root of n. So the average of all the sample means is still $200, but the standard deviation of the sample means, not of the individual orders, but of the sample means, is 30 divided by the square root of 25, or $6. So for the sample means, the mean is 200, the standard deviation is 6. So now the z is 212 minus 200 over 6, which is 2, and norm dist of 2 is 0.98. So the probability that the average of a sample of 25 orders being less than $212 is 98%. For a single order, there's only a 66% chance that it would be below 212. But for a sample, the mean of a sample of 25 orders, it's 98%. So conclusions and implications: even if a distribution is skewed, the sample means will be normal, or normal-ish. It depends on the sample size. For small sample sizes, it won't be quite as normal, but if you get up to sample sizes around 25 or 30, it starts to look very normal, even if the original is skewed. And even if a distribution has a lot of variation, meaning a large standard deviation, the sample means will have a small standard deviation, or smaller, because you're taking the original standard deviation and dividing by the square root of the sample size. And by using sample means, we'll be able to estimate the population mean well with confidence intervals. And by using sample means, we'll be able to test hypotheses. So these are the basic facts of life about sampling distribution of the mean. What happens? What do sample means look like when you go out and take a sample of some data?